It is the study of yes, carbon compounds. So we also call them organic compounds. Organic compounds are any chemical compounds that have hydrogen and carbon. Please, you're vibrating. Okay, organic compounds are chemical compounds that contain carbon and hydrogen. Okay, they can contain other elements as well, but they have to have carbon hydrogen bonds. So most of the compounds that have carbon hydrogen bonds, they will be regarded as organic compounds, except there are a few exceptions though. Like for example, carbonate, ion salts, they are ionic salts. Also cyanide, that I think you haven't come across that as yet, but you will come across them in A levels. And then another example is carbon dioxide. That is also inorganic, though they have carbon and oxygen, but they are inorganic. But other than these exceptions, generally organic compounds are compounds which contain carbon and hydrogen bonds. Okay, and study of these compounds is called organic chemistry. Now, carbon is unique from all the other elements. How? Does anybody know?
What it can get bonded with different atoms.
Sorry? Say it again. Can you please say it again?
It easily bonds with different elements.
Yes. But no. Anybody else? What makes carbon unique? What property of carbon makes it unique from all the other elements in the periodic table? You guys have completed this chapter, right? In school.
It has 4 valence electrons, so it can bond with all its electrons.
So it can bond?
With all its electrons, it can bond it with itself to form, for example, diamond.
Yeah, you see in group 4 we have other elements as well, like silicon, germanium, tin, lead. We have other, but what makes carbon unique from all the other elements of the periodic table is that it has ability to make really stable compounds by bonding with itself and with other atoms in the form of long chains. Okay, so it can repeatedly bond with itself and with other elements, especially hydrogen and oxygen. Okay, and so it forms a big range of compounds, so much so that the number of compounds that carbon can make is more than all the other elements compounds added together. So we haven't even counted them as yet completely. There are so many compounds which are unknown. So that makes carbon very, very unique. I mean, just imagine that only organic chemistry only deals with this one element, the whole. So they scientists felt the need to come up with a new branch of chemistry. Altogether, a new branch of chemistry just to deal with this one element. So this element is that unique. Okay, and it has 4 valence electrons. That means it has 4 electrons in its outermost shell which participate, and therefore one carbon atom can bond with 4 more atoms. Okay, keeping that in mind, carbon compounds are so common in nature, such as carbohydrates. Okay, now I'm going to share my screen. Okay, can I I want to share. Yes, this. Yeah, can you guys hear me? Yes. Okay. So I want to show you this. Oh, where did it go? Okay. Can anybody okay, it has. Yeah, okay, I won't ask you to recognize because they have already. Okay, can anybody recognize Oh, I cannot ask you because this is already labeled. So, okay, this is a big long chain of glucose molecules linked together. Can you see? Now, when you have diagrams like this, they don't make carbon atoms all the time, and they also don't make hydrogen atoms all the time. So sometimes they will just represent lines. So understand that the ends of lines and the corners of the lines are carbon atoms. Okay, carbon atoms are represented at the end of lines, and but I mean, if this is a ring. This is a ring, so we're only dealing with corners. But if you have single chain, I'm going to show you single chains as well. If you have a single chain, then at the ends also represent carbon atoms. So this is one ring. So can you see how carbon is making this hexagonal, beautiful ring of glucose? And many glucose are linked together. It seems as if they're holding hands together, and they form a big chain to form glycogen or cellulose, and this is a starch. Okay, and cellulose, all the plants have cellulose, the starch, we eat a starch. Okay, glycogen is inside our body. So you can see the abundance of carbon compounds. And then we have DNA. So we and most of the biological organisms are made up of long chain carbon hydrocarbon compounds. Okay, and then I also want to show you the proteins. Okay, this is a polypeptide. This is an amino acid. Many amino acids joined together. They don't have the picture. Okay, I hope you can see this. Many amino acids are linked together to form many amino acids are joined together to form big chains, polypeptide chains. So again, can you see what a big molecule carbons are making by bonding to each other? Okay, and they're also bonding to other elements such as hydrogen and oxygen. Okay, so that was the point I was trying to make. So I guess you guys already know. So if anybody asks you what makes carbon unique from other elements in the periodic table, you will say that its ability to bond repeatedly and make big long chain molecules. And it can bond to itself as well as it can bond to other elements such as oxygen and hydrogen. So after having discussed that, the compounds, yes, I need the camera back. Okay. So should I stop share? Okay, stop sharing. Huh? New share? Yeah, I did. Okay. Okay, so carbon has so many compounds that scientists needed to group them so that they can be studied more conveniently. Now, there are different ways of grouping them, and we will discuss a few of them, but let's start with saturated and unsaturated. Remember saturated solution? I hope you guys remember what does the word saturate mean? What does the term saturate mean? Any idea? Yes, Amina? Yes, Sidra? What did you say?
Saturated means no space left for new.
Very good. Yes. So when we said saturated solution, we meant that we cannot add any more solute, right? Same is the case here. Saturated hydrocarbons are those hydrocarbons which do not have any space left, for any other element, for any more atoms. No more atoms can be incorporated into the hydrocarbon. Okay, unsaturated meaning that there are some seats available for more atoms. Okay, now what do I mean by that? Let me draw. Sidra, can I have a notebook? Can I have a notebook? Okay, sorry about that. Okay, like for example, when you have Okay. Also, making structural formula is very, very easy. What is the structural formula? A formula in which you show individual atoms and how they are bonded to each other. For example, I'm taking butane. Butane is, and also you will have to learn the prefixes, how to name the organic compound. So we will come to that in a bit. Right now, I'm trying to explain you what saturated and unsaturated means. So saturated means that all these carbon atoms are bonded to each other by single bonds. Excuse me. Okay, so, okay, we don't always make hydrogen atoms. And so when you do not see any atom, assume that there is hydrogen atom. Okay, because sometimes, you know, it's tedious to make all the hydrogen atoms all the time. So we just, for example, when we make a glucose ring, we just make a hexagon like that. And so it is understood that each corner is representing carbon. And then if you have any other atom other than hydrogen, for example, OH, we will mention that. But if nothing is mentioned, then assume that it's hydrogen atom. Okay, so for example, this butane molecule. Now you can see each carbon has 4 bonds. Also make sure that each carbon has 4 bonds and hydrogen should have only 1 bond. So after you have ensured that, now, do you think any other atom can fit into this molecule? No, because all the 4 electrons of all the 4 carbon atoms have been bonded. So there is no space for any other atom. So this is said to be a saturated hydrocarbon. This is an example of a saturated hydrocarbon. Now, what is unsaturated? Double bond. Unsaturated meaning more than 1 bond, that there is more than 1 bond present in the molecule. So there is some seat available. Also, think of these multiple bonds as seats available for atoms to sit on. Okay, so again, double check. All the carbons have 4 bonds? Yes, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, you can fill them up with your hydrogen atoms or just, but you guys should write hydrogen atom in your exams. Okay, the examiner will not assume that it's hydrogen atom if you don't mention it, because you are students, you have to. I was saying that for diagrams that you might see on the internet or in the book. Okay, but you will have to mention all the hydrogen atoms. So now this is what, how will we name this? This is an alkene because it has a double bond. Okay, and it is unsaturated. Why is it unsaturated? Because this bond can break, and when this bond will break, you will have 1 electron from each of these carbon atoms available to bond with another atom. So this bond will break, no longer exist, and then 2 more hydrogen or some other atom like bromine or any other atom can come and attach here. And so this is an unsaturated, so we will call them unsaturated hydrocarbons. So remember, whenever you have multiple bonds in a molecule and it's a hydrocarbon, we call it an unsaturated hydrocarbon. They can be double, they can be triple, they can more than 1. If a molecule has even more than one bond, it's called an unsaturated hydrocarbon. What? Okay, I'm not using the chat box. Kindly raise your hand and I will unmute you. Okay, I cannot follow the chat box. Okay, raise your hand. Muhammad, what's the question?
You just explained it.
I explained it? Okay.
Yes.
Okay, good. Okay, so so remember to think of a double bond as a seat for 2 more atoms to sit on. One extra bond is seat for 2 more atoms. Remember this, 1 extra bond is seat for 2 extra atoms. Okay, another thing. Yes, another thing. Why is it that this bond is not breaking? That was a question that came to my mind. So see this, remember, carbon-carbon bonds are really stable and they're very strong. It's very hard. You need a lot of energy to break this bond. But when you have double bonds, remember, bonds are nothing but electrons, right? Bonds are nothing but electrons. When you have double bonds, how many electrons are involved here? 2 in this bond, 2 in this bond, right? 2 here, 2 here. There are 4 bonds in this small space. There are 4 bonds confined in this small space. So there's a lot of repulsion. They are similarly charged. They're going to repel each other. So there's a lot of repulsion. Therefore, this extra bond is weak. And so it can easily be broken. But if you have a saturated hydrocarbon like this, which does not have any double bond, all these bonds are real stable, and you will need a lot of energy to break them. And so they will not accept any new reactant. They will not accept any new atoms. And therefore, if you react this with bromine, bromine will not react with it. But here bromine can easily react. So we will go into the details of the reactions of alkanes and alkenes with bromine. But right now I was explaining you saturated and unsaturated. Okay. So now another way of grouping these hydrocarbons is according to the number of double bonds that they have. Okay. Number one group that we are going to deal with are alkanes. Alkanes have all single bonds, simple bonds, single bonds. Let's make a few alkanes. Let's make a few alkanes. 1 carbon. Carbon has to have 4 bonds. Let's fill them up with hydrogen atoms. Okay, then 2 carbons. Now, each carbon should have 4 bonds. So let's fill them up all with hydrogen. Okay. And you can go on making. Okay. 3 carbons. I'll just make 4 till 4. Okay. And I'm not filling them with hydrogen because that will take a lot of time. Okay. So now this is the family of alkanes. Alkanes. Okay. Okay. Now, also, then now let's talk about their general formula. Okay, another thing, there are 3 types of formulae: structural, empirical, and molecular. Can anybody real quick differentiate between these 3? Structural, molecular, and empirical. Tell me the difference between these 3 formulae. Yes, good job. Okay, Hala?
The structural formula shows all the bonds present in a compound,
Yes.
and the molecular formula is the
Wait. Yes, the structural formula definition is right. It shows all the formulae in a molecule. It shows how the atoms are bonded to each other. Don't forget to say that. Structural formula shows how all the atoms in a molecule are bonded to each other. Like, for example, somebody can write H4C for this, right? But this does not show how the atoms are bonded, right? Now we want to show that it is the carbon which is bonded to all the 4 hydrogen atoms. So this is what I mean, right? Okay. So can you say it again? Structural formula is a formula which shows how atoms are bonded to each other. Okay, Hala, did I scare you?
yes.
Okay, so now molecular formula. Hala?
It is the smallest ratio of 2.
That's empirical. That's empirical. Yes, say it. It's okay. If we are wrong, it's okay. Okay, Amna?
Yes, molecular formula represents all the atoms present in the molecule, and empirical formula represents the simple whole number ratio.
Yes, simplest whole number ratio. Like, okay. For example, let's see what is the, now, so these are what? What have I drawn this?
Structural formula.
Structural. Yes, these are all structural formulae. Now, if I want to write molecular, what would be the molecular formula for this? The molecular formula for this will be
CH4.
CH4.
yes, Zaran, CH4. Okay, what about this?
C2H6.
C2H6. What about this? Myra, Muhammad? Come on, easy enough. Just count and tell me. C3H6, C4H8. Sorry, C4H10. You know the beautiful thing about organic chemistry? Yeah, the easy thing. Yeah, the easy thing for organic chemistry, which is not in inorganic chemistry, is that organic chemistry is really predictable. They are following a pattern, they're following rules. There are very few exceptions. They don't have exceptions like inorganic chemistry. I mean, all you need to deal with is carbon and hydrogen. That's all. In inorganic chemistry, you have all these weird names and you have all these, weird elements that behave so differently. Here in organic chemistry, I find organic chemistry so easy. It is easy and interesting. It just follows a pattern. Just know the rules, know the pattern. All they're doing is following that pattern. Now, so can you see a pattern here? What's happening? Can we come up with a formula that will help us in predicting the number of hydrogen atoms? What's the hydrogen atoms per carbon atom? Is there a formula? It's called a general formula, which is, so if we have CX, H will be 2X plus 2, right? Where X is the number of carbon atoms, or you can say CNH 2N plus 2, where N is the number of carbon atoms. What? 8, 6, 7, 8. Oh, yes. Thank you. Yes. So 2 2s are 4 plus 2, 6. 2 3s are 6 plus 2, 8. 2 4s are 8 plus 2, 10. Right? So this is the general formula for alkenes. Okay. Okay. So, so we will call this a homologous series. What is a homologous series? A homologous series is a family of compounds that have similar chemical properties, and they have a pattern in physical properties as well. Right now, we won't say exactly same physical properties because their physical properties differ, but there is a pattern, and we will discuss them later. See, physical properties depend upon what? Does anybody remember? Physical properties depend upon? Sundas?
There's bonds between them, so the melting and the boiling points.
The bonds between, yes. Yeah, zor se bolo beta. Yes, intermolecular forces. Remember, physical properties always depend upon between the molecules, the forces that are between the molecules. And that has to do with the molecular mass. And can you see the molecular mass is increasing? They don't have the same molecular mass. So because their molecular mass is increasing, therefore their physical properties, which include boiling and melting point, will also increase, and we will discuss that in detail, and it will have a pattern. Okay, now let's discuss another homologous series, which is alkenes. Now alkenes have what are alkenes?
Such unsaturated compounds with double bond.
Yes. Can alkenes have more than one double bond?
No.
Okay, why
Yes.
not? Why not?
Then they're
Yes.
not called alkenes, they're called some
Yes,
alkynes, I guess.
you are partially correct. You are half correct and half incorrect. Yes, they can only have one single bond, sorry, one double bond. And if they have more than one double bond, then they are no longer alkene, but they belong to another homologous family, which is called diene, that we are not doing. Okay, but just wanna mention that alkenes only have one single bond. So no matter how long the hydrocarbon chain, even if they have 12 carbon atoms, the single bond will be only one. Okay, what about alkynes? What are alkynes?
They have a triple bond.
Very good, they have triple bond. So do they have only one triple bond in the whole molecule, or can they have more than one? Can they have more than one triple bonds?
No.
No. Again, if they have more than one triple bond, they will be belonging to some other homologous family, right? So so we can group them according to the number of double bonds that they have. Okay. Okay. Let's draw. Yeah, but it will disrupt me, right? Okay, if you can do it without disrupting me. Okay, so now you cannot have an alkene which has only one carbon atom, right? Why is that?
Because they need to have a double bond between two carbon atoms.
Right. And so, I mean, at least they should have two carbon atoms. So we will start with two carbon atoms. We will, yeah, I'm trying to change my camera. Okay, so excuse me for any disruption. Okay, so let's start with two carbon atoms. That's the minimum an alkene can have, right? And so make sure that all the carbon atoms have 4 bonds. So this is my first alkene. Okay, how should we name it? What should it be called?
Ethene.
Yes. Now also let me talk about prefixes a little. Now these prefixes are used to name the hydrocarbons depending upon the number of carbon atoms that they have. It is helpful to memorize them. Meth is the prefix for one carbon atom. What is, okay, but this is inverted. Can you see my video is inverted, right?
No.
No, it's not.
No. Oh, okay, excuse me. Yes, it's, yeah, now it's fine. Yeah, it's inverted. That's why I was telling you, don't do it right now. Can you, is my video inverted? I mean, laterally inverted.
No, it's straight.
It's a straight?
Yes, miss.
Yes, miss.
Okay, then leave it. You know, but it's inverted for me. It's inverted for me, it's going to confuse me. Okay, so prefixes, it's useful to learn the prefixes. Okay, one, meth, when you have one carbon atom, meth, two carbon atom, eth, ETH, 3, pro, 4, bute. Okay, so you have propane, ethane, methane, butane, then 5 is penta, pentane, and then you have 6 hexa, and then you have 7 hepta, and then you have 8 octa, nona, deca. You have for 11 and 12 as well, but un and dodecane, undecane, so on and so forth. So learning these prefixes is helpful. Okay, we will talk about naming in detail later. Okay, just like our names have first names and last names, right? So our last names are usually our family names, right? Like, for example, my name is Quratul and Bukhari, right? So Bukhari is my family name. So everybody's name has two parts, last name and first name, right? So these compounds also have first and last names. Last name is their family name, which is their homologous series, which is the name of their homologous series, whatever they belong to. And the first name depends upon how many carbon atoms they have. For example, how will we name this? So because it has two carbon atoms, the first name will be the prefix et. Pre means coming before, coming first in the beginning part of the name, prefix. So et in, and they will end in "ene" because it belongs to the alkene family. So "ene" is the family name, the last name. So ethene. Okay, if this was alkane, then it would have been ethane, and so on and so forth, right? Okay. Now, if we have 3 carbon atoms, and then you have double bond, okay? Now, the rest of the bonds will be taken by hydrogen atoms. So how will we name this? Can anybody tell me? How will we name this?
Propene.
That's it, propene. Okay. Yes. Yes, it will be propene. Okay, now how will we name this? And just to know that the rest of the bonds are filled by hydrogen. So how will we name this?
Butane.
Butene?
Butene.
Okay. Okay, now if this is butene, then what is this? What is this?
It's also
Butane.
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 It's an isomer.
Okay, good. So, but then if you're talking about this butene, but the other person is thinking you're talking about this one, how will you tell him which butene are you talking about?
Butane.
Then we further name it butane and butene.
So, beta, this molecule's name is not just butene. You will call it but-1-ene or 1-butene. Both are correct. Okay. So now, what are the rules that we are following when we are naming these organic compounds? Is that, remember, as we have already talked about the last names and the first names, right? First name depends upon the number of carbon atoms. The last name depends upon the family. And then if you have any functional group, which in this case is the double bond. What is a functional group, by the way? What's the definition of a functional group? What's a functional group? Does anybody know what a functional group is?
The double bond.
Loudly, beta, loudly. Yeah, double bond is the functional group, but I want to know the definition. Yes, yes, you are right.
The part of the molecule that participates in
Ma'am,
the
maybe which differentiates the hydrocarbons from one another.
Yes, yeah, you guys are correct. That group of atoms that is responsible for the chemical properties of that homologous series. Okay, a group of atoms that is responsible for the reactions or the chemical properties of that particular homologous series. So what makes this the alkene family different from other families is this double bond. Okay, so this will be the functional group of this family. So we have to mention the position of that functional group in the name. And how do we do that? I mean, we can start counting from here, 1, 2, 3, 4, or we can start counting from from the left-hand side, 1, 2, 3, 4. So now what to do? So there are different ways of even numbering the carbon atoms. So scientists have agreed that we will count in such a way that the functional group should get the least number. Okay, so like, for example, in this case, we could have started counting from here And then this would be but-4-ene. But that is against the convention. The convention meaning the rules that we have to follow, is that we should number the chain in such a way that the functional group should get the smallest number. Okay, so we will start from here because the double bond is on the first carbon atom. 1, 2, 3, 4. And then of the 2 carbon atoms which are involved in the double bond, which one should we mention? The one with the smaller number. Okay, so we will say but-1-ene, not but-2-ene. Okay, now in this particular case, it doesn't matter whether we start counting from right side or the left side because it will be 2. So this is but-2-ene. This is but-2-ene. And yes, you are right, they are isomers. Okay, they are isomers of each other. And so they are different compounds, meaning that though they have the same atoms and same number of atoms of each type, but they will differ in their physical as well as chemical properties because of the difference in the arrangement of atoms. And that we will discuss later. Okay, so okay, let's name a few. Let's see if you can name this. Let me make this a little confusing. How will you name this? Name this.
Hexene.
2-hexene.
Hex-2-ene.
Very good. Yes, 2-hexene or hex-2-ene, right? Hex-2-ene, right? This is the correct answer for this. This is the correct name for this compound. Okay, then let's move on. So we will not discuss alkynes that much. Alkynes are not included in IGCSE that much. Okay. Now, remember, homologous series is a family of organic compounds that have the same general molecular formula, similar chemical properties, and they have gradual increase in melting and boiling points. Okay, naming of organic compounds I have already done with you. Okay, let me see. Okay. Structural general formula. Okay, so what is the general formula for alkenes? Let's see.
CnH2.
Yeah, are you convinced? Did you work them out? Did you work them out? Can you please turn the fan on? Did you work, like for example, this is ethene. So this is C2H4. So what we can see here is that hydrogen is twice the number of carbon atom. So we can easily say CnH2n, but let's verify. Let's see if this is true in case of propene. 1, 2, 3, 1, 2, 3, 4. So, okay, how many carbon atoms? 1, 2, 3. How many hydrogen atoms? 1, 2, 3, 4, 5, 6. So yeah, here as well, hydrogen is twice the number of carbon atoms. Let's try out with butene. And so try with a couple of, and then be convinced that this is true. So C4, 1, 2, 3, 4, 5, 6, 7, 8. So that means the general formula is CnH2n, okay, where N is the number of carbon atoms. Okay, and then we have alkyne general formula as well, but I don't think it is required, so let's just skip it. Now let's talk about melting and boiling points. Okay, what do you know about melting and boiling points? What's happening to the melting and boiling points of the hydrocarbon? Any ideas? Remember, the physical properties depend upon, I'll give you a hint. Physical properties, always remember this. Physical properties depend upon the, complete my sentence.
The intermolecular.
Yes, very good job. Now, how can you see my video? Is it upright?
Yes.
It's absolutely fine.
Yes.
Okay, good. Okay, Alhamdulillah. Okay, they cannot read. Can you read? Can you see these numbers at least? If you cannot see my camera, then take out page 255 in the book. Take out page 255 in your book. I want you to see this table. Sorry. No. Just don't do this. Okay. What's happening to the boiling point? What's happening to the boiling point? It's increasing. Okay. It's increasing, right? So why do you think it's increasing? Any explanations?
Because the intermolecular forces start getting stronger.
Very good. Why are they getting stronger?
The number of bonds is increasing.
Number of bonds is increasing. Why?
The number of carbon atoms.
Yes. Okay. So how is that increasing the intermolecular forces? How is the number of carbon atoms increasing the intermolecular forces? Beta, explain me as if I don't know. Explain me. Like I explain you guys. It's okay. I think you have the idea. You are right. But explain me more. Come on. Hamza, Hala, Ajwa, Ahmad.
As the carbon atoms increase, there are more hydrogen which get bonded to the carbons.
Okay. So was this discussed in your classes? Were these things discussed?
Yes, Miss. Our teacher just told us that the boiling
Okay.
points increase because the carbon number of carbon atoms increase.
So did you guys ask why, how? Did you understand? Beta, koi to jawab do, beta.
When the number of bonds increases, so the intermolecular forces increase because they have to keep all the hydrogen atoms together.
Okay. Okay. No, beta, this is not the explanation. Okay, let's talk about in detail. Okay. Now, yes, you are right. So far, you are right that the intermolecular forces are responsible for the physical properties, be they be solubility or a boiling point, melting point, densities. All these are physical properties and they all depend upon intermolecular forces. Now, we are particularly talking about boiling and melting point. Now, what's happening in boiling and melting? First of all, understand the process. What's happening in melting and boiling point? We all know, right? Now, come on, answer this question. Explain melting real quick and boiling real quick in 1 or 2 sentences. So
the forces of attraction are being weakened.
Very good. And then?
So that the atoms are broken apart.
Atoms or molecules?
Molecules. And so the state changes.
Yes. So in melting, the molecules are getting farther away from each other, right? They're losing their fixed arrangement. They are now random and their motion is increasing. They're going farther away from each other. The distance between them is increasing, right? So you get the point that, that's melting. And then gas, boiling is turning into gas. So gas, they're getting free. They're breaking free of their attractive forces between them. And they are now free to escape in the gas or in the air, right? So they are turning into gas, right? So that's what's going on in melting and boiling point. So the thing they are fighting against are these attractive intermolecular forces. As soon as they can get free of these attractive forces, the melting and the boiling process will ensue. So stronger these forces, more energy required to break them or to weaken them. Remember, in melting, you are just weakening the forces. In boiling, you are completely breaking them, right? I hope you already know this. So of course, boiling will require more than melting, will require more energy than melting. So now here we are, so we understood this when we were in organic chemistry, we were talking about ionic compounds and we were talking about the polar compounds. But here in organic chemistry, we are talking about hydrocarbons. We are talking about hydrocarbons. Now looking at their molecule shape, I mean, they are not exactly shaped this way. This is just a structural formula, but looking at the arrangement of atoms, you can have a rough idea. What sort of molecules are they? Do you think they are polar? What is polarity? Does anybody remember? What is polarity? Sandos? Come on, tell me, what is polarity? Loudly.
It's the uneven distribution of charge over one molecule.
Yes, uneven distribution of charge. Okay, so when you have what do you mean by uneven distribution of charge? Meaning that one part will have, for example, this is a molecule. I made a rough diagram, rough. You have positive in the center because of the nucleus, and then you have electrons revolving them. So basically, you have positive charge at the center, and then you have electrons around it. You have negative charge around it. So if these electrons are uniformly distributed, that means the charge is uniformly distributed, and so you have no separation of charge. No separation of charge, right? But because hydrocarbons are this way, they are nonpolar, meaning all the charge is uniformly distributed. Okay, all the charge is uniformly distributed. Why is that? Why are hydrocarbons nonpolar? Why do you think hydrocarbons are nonpolar? Because why are hydrocarbons nonpolar?
Because
Yes, Amna. Because
they're evenly distributed.
Yeah, why are they evenly distributed?
Because the atoms are placed evenly away from each other. Like the carbon atoms.
See, let me tell you, I have discussed this already, but let me explain this again. When you have a more electronegative, for example, let me take the example of oxygen and hydrogen. So when you have one very highly electronegative element and other, you can call it electropositive or very weak electronegative, or you can say electropositive, relatively electropositive element, bonded together, what does it mean? That it is snatching away the electron cloud more towards itself. So like, for example, this is an electron cloud. Okay, think of electrons as clouds. I told you electrons behave as waves, and they also behave as particles, but they also behave as waves. Okay, so if they are like clouds, so the cloud is pulled more towards the electronegative element. So can you see that now the charge is unevenly distributed? This part of the molecule has positive and this has negative. Okay, but this is temporary. Temporary meaning that this cloud, because of the movement, this cloud can momentarily move here and there. So when it does that, the partial charges also move here and there. So because of their movements, this charge can get more on one side momentarily and then get back to its original position or move to the other side. Okay. So the thing is that when you, the reason why hydrocarbons are nonpolar is because in hydrocarbon, you have carbon and hydrogen. You have bonds between carbon and hydrogen, and there is not much difference in the electronegativity of carbon and hydrogen. They are not, the bond is nonpolar, meaning both are almost equally pulling the electrons. Okay, so no one element has more electron cloud than the other. So there is no separation of charge. Do you get me? Did you guys understand this? So carbon
Yes.
and hydrogen, yes. So remember, this is very important. This is so important. Why are hydrocarbons non-polar? This will help you if you understand this polarity concept. This will help you in biology, chemistry, everywhere. You will understand why non-polar substances dissolve with non-polar and polar with polar, and why is it that polar substances do not dissolve non-polar substances. So remember, hydrocarbons are non-polar because carbon and hydrogen are equally pulling on the electrons, and therefore the electron cloud is uniformly distributed. There is no separation of charge. So hydrocarbon molecules are overall like this, uniform distribution of charge, because carbon and hydrogen both are pulling on the electrons almost equally. But what happens is that as their size increases, they become bulkier, right? And remember, each atom is with electrons. Each atom is with electrons. So more the number of atoms, more the number of electrons, bulkier they get. And so when they move, when they are moving, and remember, these electrons are constantly revolving, right? So there are times when momentarily the electron cloud is pulled to one side, okay? And so one part of the molecule gets positive charge, partial positive charge, and the other gets partial negative charge. That in turn induces polarity in the neighboring molecule. And so the positive one attracts the electron towards itself. Okay, and so you can see the electron part is pointing towards the positive side of the neighboring molecule. And so there is some attraction, intramolecular forces of attraction, which are called van der Waals forces. These are called van der Waals forces. And remember, this effect is more pronounced bulkier the molecule is. Bulkier the molecule, the stronger the van der Waals forces. Why? Because, see, more the electrons, the longer it will take for it to come back and become non-polar. So when it becomes polar, it will stay polar for some time. And so that will make these attractions stronger. Are you getting me, Sandus? Yeah, so remember, more the molecular weight of a molecule or an atom or whatever you're dealing with, stronger the van der Waals forces. Now, what are van der Waals forces? Van der Waals forces are weak intermolecular forces. They can be of attraction, they can be of repulsion, and they are because of this whole phenomenon, you know, the movement of the electrons, which is temporarily more on one side of the molecule than the other. Like, for example, if for example, when the molecules are randomly colliding, if you get another molecule which by mistake had, because of the motion, had negative charge come close to the negative part, negative, and this is also negative. When the negative part of a molecule comes close to the negative part of the other molecule, then there will be instant repulsion. That repulsive force is also called the van der Waals forces. This is attraction because there are opposite charges involved here. So this is attraction. So van der Waals forces can be repulsive, can be attractive, depending upon what parts of molecules are interacting with each other. Okay, so I hope you understand that. Now, there are some hydrocarbons that have polar functional groups, like, for example, alcohol. Alcohol. What is an alcohol? Alcohol's structural formula is ethanol, 2 carbon atoms, OH, this is ethanol. Okay, now can you see the highly electronegative oxygen is sitting in there? So because of this oxygen will tend to pull the electron cloud towards itself. So the electron cloud will be this way. The electron cloud will be more towards the oxygen part of the molecule. Why? Because oxygen is electronegative. It is pulling the cloud more towards itself. So now this molecule is going to be polar. And not only due to the motion, but because of this electronegative oxygen. Therefore, the intramolecular forces between the alcohol molecule, for example, this is another alcohol molecule. Okay, and this is its positive part of the molecule, there will be attractive forces, van der Waals, and these will be really, and by the way, these forces are so strong that they are no longer called van der Waals, they are called hydrogen bonds. And you have hydrogen bonds even in water. So remember, whenever oxygen is involved and whenever oxygen is bonded to hydrogen, whenever hydrogen is bonded to oxygen, nitrogen, or fluorine, you have hydrogen bonds in between the molecules. Hydrogen bonds are really, really strong. Of all the intermolecular forces, hydrogen bonds are the strongest. Okay, and the hydrogen bonds are responsible for water's high boiling point, which is 100 degrees Celsius. Okay, so now we understand why the boiling point is increasing as the molecular weight of these molecules is increasing down the group. Okay, now did you understand? Now, if anybody asks you why is the boiling point increasing, how will you explain this whole story in a concise, summarized manner? How will you say? This whole story that I just explained you, can you summarize it in like 2 to 3 sentences? Sundar?
Hydrocarbons are polar, so
Polar? They're non-polar.
non-polar. So the van der Waals forces increase as the
Very good.
as the bonds increase.
Yeah. Yes.
And so the physical properties increase down the group.
Yeah, see, you're going to say in 2 to 3 sentences, if you ask me, I will do it this way, that as we are going down the group, I mean, down this homologous series, the molecular weight is increasing. And so as the molecular weight increases, the number of electrons in a molecule increases. And so more polarity is induced into the molecules, and that gives them stronger van der Waals forces. And then when they ask you what are van der Waals forces, then you're going to say that van der Waals forces are intermolecular forces which are due to the molecules interacting with each other. So they can be repulsive, they can be attractive, depending upon what part of molecule is interacting with the other. Okay, I hope I made sense. Is there anybody who did not understand? Then raise your hand and ask me questions. Is there any questions so far?
No, Miss.
Did you understand? Okay, so this phenomenon, I'm going to take 5 to 10 minutes extra because we wasted a little time. I'm sorry. Okay, so this phenomenon is also seen in halogens. If you look at halogens, the first 2 halogens, fluorine and chlorine, are gaseous. Okay, their boiling point are in negatives. Okay, but as we are going down, bromine is a red color liquid. The boiling point is 59 degrees Celsius. And then iodine is a purple color solid and its boiling point is 114 degrees Celsius. Also appreciate how their molecular weight is increasing. So what's happening? Same thing. Same thing. They are getting bulkier. And because they are bulkier, their number of electrons in a molecule is increasing. And as the number of molecule is increasing, they are acquiring a stronger polarity, stronger intermolecular forces, or stronger van der Waals forces. Now, let's talk about the boiling point of these 2 molecules. What are these? This is a line diagram, by the way. I told you this is 1 carbon. This is 1 carbon, this is 1 carbon, this is 1 carbon, and all bonded to hydrogen atoms. Okay, I did not make all the carbons and all the hydrogen atoms. So this is a butane. How many carbon atoms? 1, 2, 3, 4, butane. Okay, if there was any functional group, I would have mentioned, so that means only hydrogen atoms. This is nonane, 9 carbon atoms. 9, yeah, no? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Which one is going to have a higher boiling point and why?
Non-N will have a higher boiling point because there are more intermolecular forces.
More van der Waals forces. Okay. Okay. Another thing, look at this. Look at this. Because the molecule is so big, can you see? more interaction between the molecules, more van der Waals forces working between the molecules. Here, the molecule is small and therefore less van der Waals forces, and it's easier for them to move away from each other. Okay, so get this intuitive that bigger the molecule, bigger the boiling point. Okay, higher the boiling point. Okay, now compare these two molecules. This has this oxygen atom. This has no oxygen atom. Which one will have a higher boiling point?
The one with oxygen.
The one with oxygen.
Why?
Because oxygen attracts more electrons. It is more electronegative.
Yeah, and so it will do what to the molecule? Yeah, make it polar. Exactly, very good. Yes, it will make this molecule polar, and because of which, stronger intermolecular forces, van der Waals forces. Okay, like look at this. This was the one with oxygen. It pulled the electron cloud more towards itself, and that, when interacted with the neighboring molecule, also attracted, it attracted the positive part of the other molecule, right? And so stronger van der Waals forces. Okay, so, okay. Okay, now if you have two molecules, this and this, let me make it so structural. Did I make it structural formula? Yes, this. Yes, look at these two. Look at these two molecules. Which one will have higher boiling point? Let's see.
The one with the oxygen.
Both have oxygen. Both have oxygen.
Maybe the one with the double bond.
Why?
The one without the double bond.
Very good. Why?
Because the single bonds are much stronger. Because they're less electron repulsion.
No. No. Remember, I'll give you a hint. I want you to answer. I'll give you a hint. Oxygen is, hydrogen is bonded to oxygen. When hydrogen is bonded to oxygen, what happens? What intermolecular forces act?
Electronegative.
You guys are not paying attention. What did I just say? I just said that when hydrogen is bonded to oxygen, nitrogen, and fluorine, what intermolecular forces do we have? See, you guys were not paying attention to me. Hydrogen bonds, remember? I said hydrogen bonds. When hydrogen is bonded to oxygen, you have hydrogen bonds, one of the strongest intermolecular forces. Of the intermolecular forces, hydrogen bond is the strongest. It's okay, beta. No need. Okay. Okay, so remember, okay, so this has hydrogen bonds, okay, because of which this is going to have greater. Okay, remember this, write it down if you need to, that when hydrogen is bonded to oxygen, nitrogen, or fluorine, because these are the most electronegative elements in the whole periodic table, you have hydrogen bonds as the intermolecular forces. Now, let's talk about these two molecules. How many carbon atoms are there? 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4. There's a fifth one. This is fifth. 1, 2, here, 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 and here. So which one will have a greater boiling point? Here, these two. Both of them are pentane. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which one will have a higher boiling point?
Ma'am, this one on the right.
The tetrahedron or the simple chain?
The tetrahedron.
Tetrahedron, why?
Because of its structure.
Beta, answer completely. What do you mean because of its structure? Yeah, what do you mean?
Actually, miss, they will both be they will both have the same boiling point because they got the same amount of because they're
Carbon.
both pentane.
Same number of carbon atoms. No, beta, no. Listen this. No, right or left में बोलो बेटा. Just say chain बताओ ये बताओ.
Miss, and the tetrapentane because of its structure. It's what's it called?
All hydrocarbons are nonpolar. I'll give you a hint. I'll give you a hint. Okay, use my hint. Look at this. What did I say? When there is more interaction between molecules, higher boiling point. So look at the shape. Which molecule do you think will interact more with its neighboring molecule?
The one with
Tetra.
the train.
The chain one or this one? Which can interact with its neighboring molecules more?
Tetra. And the one on the right.
No. How come tetra? No. This line, beta line. Look at this. They can pile up on each other. Look at this. They can pile up on each other, you know. They can be squeezed together so easily, you know. And look at them. They're tetrahedron. They are not compatible. I mean, how close can you pile tetrahedrons on top of each other? Can you pile tetrahedrons on top of each? Do you know what a tetrahedron
No,
is, right?
Yes, ma'am.
You don't know? Like a pyramid? Yeah, like a triangular, in this case, triangular pyramid, like the base of which is a triangle. How can you stack up together? Meaning that these molecules will interact more, they will have more van der Waals forces, with each other, and so they will have a higher boiling point. Okay, this one will have a higher boiling point. So look at the shapes. Okay. Okay. Okay, now let's real quick talk about the burning of the alkanes and the alkenes. Now, alkanes are very good fuels. Why? Because they burn in oxygen and to give carbon dioxide and water, and that's a highly exothermic reaction. Why is it so exothermic? Because the products that they form, remember the exothermic, endothermic energy level diagrams that we did? So lower down, the products are, meaning more the energy is released. Remember? I hope you remember those diagrams. So all this energy released is what we get when a reaction takes place, right? So remember, more stable the products, the lower down they are going to be in the energy level diagram, and that would mean more energy released. And so therefore, alkenes burn in oxygen to give a highly exothermic reaction, and they produce carbon dioxide and water, and that's why they are so valuable as fuels. Okay. And so again, can you see that methane is a natural gas? It's the cooking gas that we use in kitchens for cooking food, whereas ethane and propane, they are easier to liquefy. Why are they easier to liquefy? Again, because they have this methane, because it is such a small molecule, bringing its molecule closer together will be harder. Okay, these are a little, so this has a very low melting point, right? And they have higher melting point, close to room temperature. So they are easier to liquefy. And so they are liquefied and they are packed in containers. I think the rest we will do in the next class, and I want to complete this chapter with you guys. So the next class that I will take will be on Sunday, inshallah. Okay, on Sunday I will continue this chapter. Is there any question?
No.
Okay.
Okay.
Okay. Okay, then assalamu alaikum wa rahmatullahi wa barakatuh.
Walaikum assalam.
Thank you, Miss. Allah.
You most
Shukran.
Allah Hafiz.